So last class, we finished up with doing the root locus. And the key thing is that when we did our discussion and we looked at the characteristic equation, we saw that we had this case where when we bring our poles of our transfer function, our open loop transfer function, and we bring them up and do the common denominator approach, what we see is this expression right here. The poles, whatever the poles are, plus k times the zeros has to be equal to zeros for it to be a valid root point. And so when we did that, we started with our concept of a mantra, which is we always start at a pole when k is equal to 0. We have our poles, and then as k increases, approaching infinity, we end up stopping or ending at a 0, all right? So when we're drawing these root locus plots, it's always helpful to look because you have to identify, let's say there's a root locus that lives between those 2 points. We know that we start at a pole, we go that way, and we start at a pole and we go that way, but there's no 0 to terminate, right? And at some point, they will be basically at the same point on the real axis. And at that point, you have to exit the real axis because you still need to terminate at a 0. And so understanding where you live on the real axis, where the poles and zeros, where the roots, where they start and where they end is really, really, really helpful. Okay, so that was our second rule. All right, let's take another example here. And we see that we have open loop, so G times H, because H is in fact equal to 1. G times H is just going to be S plus 3 times S plus 4, all over S plus 1 times S plus 2. And we can see that we have a 0 at -3, a 0 at -4, and then a pole at -1, and a pole at -2, right? So this is an easier case because we have the same number of finite poles as we do zeros, right? Same number of finite poles, same number of finite zeros. So we have zeros at S approaches infinity, correct? Because we have the exact same amount. So in this case, if we're going to draw a root locus, what we would very quickly realize is that our 2 root loci, right, because we only have 2 roots, they're going to start at a pole and end at a 0. Start at a finite pole and end at a finite 0. So here's our transfer function, all gussied up. And remember, this here is our characteristic equation. That's what we're wanting to, that's what we're wanting to check the roots of. So remember, we go from 0 to a large number and watch how our closed loop poles move. All right, so let's take a look at this and see. We're starting. And what happened? We started at poles, right? We started on the real axis and we headed toward each other. At some point, we realized we're not going to be able to terminate. So we have to leave the real axis. And then at some point, we have to get back in to the real axis. Why? Because we have to terminate at 2 finite zeros. Let's try that again. Watch as the K starts, and it's going small. Now it's going to leave the real axis as I continue to increase K. It just doesn't go off to infinity, but it's going to turn back down. And then eventually it's going to go back to the real axis because we need to make sure that we terminate at a 0. We only have 2 zeros, 2 finite zeros, no infinite zeros. So we can't just go to infinity. We have to come back. All right. So even just by looking at this, I know that my diagram or my pole zero map, I knew it was doing this and doing this. And then I had to eventually come back this way and get back onto the real axis and terminate at those two zeros because of the rule starting at a pole and ending at a zero, right? So this is okay in terms of, what we have to understand, but the problem is I need to know what that point is. Okay, I need to know where it leaves the real axis, and then I need to know where it enters back the real axis. Okay, so it's important when we'll go ahead and develop that in a bit. But this shape right here, that shape we just have to get over time. We just learn how to get it over time. If you want to get its exact shape, you just have to actually start finding points, like do it manually like we just did. But if you know that it starts over here, you can approximate what the root locus looks like. And then you can see, okay, is this a valid point by checking that 1 plus kgh, does that equal to 0? So what happens if we have more poles than zeros? Let's think about that. We have more P's than Z's. So let's take a look at that example again. So if we have more poles than zeros, let's assume that we only have one finite zero. What has to happen? Brandon?
One of the poles would be infinite.
Infinity, yeah. So when we include infinite poles, we have two finite poles, one finite zero, and one infinite zero. So based on that, where do you think that root locus is going to go? It still has to start at a pole. And so we know we're going to go like this, right? The problem is that I only have 1, 0 to terminate at, right? How many root loci do I have? 1, 2, right? I've got 2 of them. So where does that other root loci terminate at? Way out over S approaches infinity. Okay. So I have to have 2 root loci because I have 2 poles, and I have to terminate at 2 zeros. So I terminate one at the finite pole and the other one at the infinite pole, the finite zero, and the other one at the infinite zero. Now, over here, we have to have complex conjugate pairs, right? So you can see all along here, I have complex conjugate pairs. Once I get back onto the real axis, there is no complex conjugate, right? Because there's no complex number associated with it. So even if this one is going someplace over here, I don't have to have a plus or minus 5 or something like that because I don't need to have complex conjugates. I just go ahead and I can do my numbers. All right. So the question is, how do I approach those zeros? Well, this one I can see that I'm approaching it at 180 degrees. And so what we have to do is we have to calculate what are called asymptotes, angles of the asymptotes. Because if you remember from math, an asymptote is if you allow a number to get really large, like as k approaches infinity, that's eventually what the root will get to. So here's our characteristic equation. We have more open loop poles than open loop zeros. Let me move this up over here. The open loop transfer function approaches 0 as S approaches infinity. So we're going to do our limit function here. And we end up with that, right, by doing our limit function. Near S approaches infinity. Here's what we have, right? We have S to the M plus KBM, right? When we move this term up over here to the numerator, we have 0. then we can solve for our K term here, or our KB term. And B is just a coefficient, right? It's just a random coefficient. And we can see that S to the N minus M, this is the order of the numerator. That's the highest order S term in the numerator. This is the highest order S term in the denominator. The difference between the two is going to tell us the number of poles or zeros at S equals infinity. And you can see that S to the N minus M, the number of poles, has to equal negative K over B sub M. And that's going to be equal to this value of R. So R is going to be essentially equal to that value of N minus M. Well, remember, the only way I can get a negative number has to be equal to plus or minus 180 degrees, right? This is plus 180 or minus 180. And so what I'm going to do now is I'm just going to go ahead and calculate the angle of the asymptotes using this equation here. So I have S to the N minus M is equal to the magnitude of KB at an angle of R times 80. I'm really only interested in the angle of the asymptotes. So if I have one asymptote, I have the angle of the asymptote is equal to R times 80, because again, R is equal to N minus M. So if R is equal to N minus M, 2 minus 2, then R is equal to 0. I don't have any angles of asymptotes. If R is equal to 1, I have plus or minus 180. If it's equal to 2, then I have plus or minus 90. Does that make sense? Let's say that I have 2 poles and no zeros. Okay. So I'm starting my root locus by leaving my poles. And I want to end up at zeros. Will I jump back onto the real axis? Do I have a 0 over here? I don't, because if I'm doing N minus M equals 2, which in this case has to be equal to my 0, right? So I have no finite zeros. So I'm not going to ever go back onto the real axis, am I? So in that case, my root locus does this. It goes in that direction. This angle is 90 degrees, right? Plus or minus 90 degrees. So I'm just going up or down at 90 degrees. If I have a difference of 3, then it's going to be plus or minus 60 and plus or minus 180. All right. So if it's plus or minus 60, then I have here, right? I have 3, and we're just going to start there on the real axis. So I have 3. So these two will head this way. This one, okay? Well, let's do this first one. So these two are going to head up in this direction here at plus or minus 60 degrees. What about the other one? This root locus, I know, is going to start at a pole. Where does it go? I think we have our thinking caps on. Where does it go? It has to approach a 0, right? As my K gets bigger and bigger and bigger. So where does it go? Does it leave the J omega axis? I mean the real axis, not the J omega. Why not?
I can't explain why not, but I feel like I remember seeing a problem with
You're right, it can't leave the real axis. And maybe you have seen a problem, but what's the reason why you can't leave the real axis? Anybody in TV land? Separation, I'm not quite following you.
120 degrees that way, 120 degrees that way.
Well, that's for three-phase systems, so that wouldn't apply here. Let's see if we presented it thus far. I wonder if there's anything on this slide that perhaps would tell me why we can't leave the real axis. Is there perhaps a rule that you maybe see as to why you can't leave the real axis? It's symmetric about the real axis, right? Why is that? So we're symmetric about the real axis. What's another way to say that? We have to have complex conjugates, right? Always. You can never have a number over here without a number over here. And why is that? Because remember the quadratic equation? Negative b plus or minus the square root of b squared minus 4ac all over 2. If we have complex numbers, then what we have is plus or minus j times, let's see, AC minus b squared over 2 squared. This has to be a complex number. You have to have a plus j and a minus j, don't you? So anytime you have a complex number, it must be complex. So this tells me right here, I can never leave the real axis, can I? Because I don't have 2 roots there. I only have 1. So this one has to approach way out as k approaches infinity. Our s are infinite at 0. All right. So that's why we got 60. Let's see if I can erase this. Guess I can't erase it because it was there before. And plus or minus 180. The 60 means I'm going over in this direction, someplace over here. And the 80, the plus or minus 180 means I approach as s or k approaches infinity. Now, one thing to note, if these poles are all in the right-hand half plane, you know, as long as I stay in the left hand half plane. If all those poles are in the left-hand half plane from the start, they're going to stay there. Over here, you can see eventually I'm going to have an unstable system, aren't I? Because as I approach at plus or minus 60 degrees, I actually cross the j omega axis, and so I will have an unstable system. So I can't just increase k indefinitely so that I get whatever value I want. At some point, it's going to be an unstable system. All right. If you have 4, then you're going to go ahead and you have plus or minus 45 degrees and plus or minus 135 degrees. Okay. So you'll have 2 that cross the j omega axis and 2 that go in the opposite direction. And we're not going to go ahead and do the math for this, but the way to solve where those asymptotes intersect the real axis is here. You take the sum of the finite poles, you subtract the sum of the finite zeros, and then you divide by n minus n. All right, so that's our third rule. Rule number 3. If you have n minus m, and it's a positive number, then you've got asymptotes, okay? And you want to go ahead and calculate your angle of your asymptotes, as well as the center of where those asymptotes originate from. And you have that center originates is applicable for all of those asymptotes. All right, let's take a look at an example. So we can see that this is, when we're all said and done, this is S to the M, which means it's a first order, right? We only have one S over here. Over here, we have four S's that multiply together. So S to the N is equal to S to the fourth. Now we can define R, which is equal to N minus M, which is 4 minus 1. That means we have 3 asymptotes, right? We have 3 asymptotes because we have 3 roots that are going to approach S at infinity as K increases. So you should have 3 of them. So we have R, which is going to be equal to plus or minus 1. And then we skip and go to plus or minus 3. So our angle of our asymptotes plus or minus R times 180 over 3. Because again, this is N minus M. And we have plus or minus 60 and plus or minus 180 degrees. Right? So these are the angles. Now I've got to go ahead and calculate where I take off or where my asymptotes are centered about. Now, here's where you got to be careful. What is the zero of this open loop transfer function? What's the zero there? -3. It's not +3, it's -3, right? Because a zero is what you plug in to make it force it to 0. Or it's the root of the numerator. So I have -3 is my 0. And my pole, or poles, I have 0 for this one, -1 for this one, -2, and -4. And those are the finite zeros, right? And finite poles. I also have 3 zeros at S approaches infinity, correct? Because I always have the exact same number of poles as I do zeros. So now I'm going to go ahead and calculate what my not sigmoid, but my center point for my asymptotes, and I end up with -4/3. Okay. So if I'm going to draw those, I will draw. And this is just a suggestion for how to start drawing these things, but I find it really, really helpful to draw them this way. So I put my pole zero map here first. All right. Now I'm going to go ahead and show my roots. So I have 1 at 0, 1, I believe, at -1, 1 at -2. Then I have 1 at all the way out here at -4. And then my 0 is right here in the middle, right? It was S plus 3. So -1, -2, -3, and -4. Let me just double check to make sure. Yes. All right. So now I'm going to go ahead and start to see, well, I'm leaving here. And I realize that I'm not going to be able to terminate, right? So I have to get off the j omega axis. Well, -4/3 is someplace over here. So now I'm going to draw my asymptotes, and I'll draw those as dashed lines here and here, and that's plus or minus 60 degrees. These two leave someplace and then approach the asymptotes as K approaches infinity. Okay. Now there's another one at 180 degrees, right? So we had plus or minus 60 and 180 degrees. So this one's going to be a little bit harder to see. I'll put a different color. Hopefully this is legible. But this is the one that's at plus or minus 180 degrees, right? It's on the real axis. But you won't be able to see it because why? Because it just, you know, it's on the real axis. So now this one leaves a pole and ends at a 0. Well, what do you know? On the real axis, I actually have a 0 to end my root locus. So that ends right there. The last one starts over here and goes all the way out and approaches at s equals infinity. Okay? So our rules are still met, right? Start at a pole and end at a 0. So we got zeros way out over here someplace as s approaches infinity. So we started at a pole, we started at x's and ended at zeros. So check for those two root loci. Started at a pole, ended at a 0, check. Started at a pole, ended at a 0, check. Our base rules for drawing those are being met. Okay? So you do have three root loci, but you know when you have one at 180 degrees, you don't even have to bother drawing it because it stays on the real axis. It doesn't deviate from it. All right? Questions on that?
I got a quick question.
Yes.
Is there ever a case where two poles go to the same 0?
Excellent question. So the question was, is there ever a case when you have two root loci, I guess, that ever terminate at the same 0? And the answer is sort of, right? And what I mean by that is over here, you can see these are two different points, right? This is point 1 and this is point 2. But what we said is as s approaches infinity, these become zeros, right? So we don't really have a definition for what that number is. We just said as s approaches infinity. So you can say way out at infinity, they do approach those points, but they are separate points. So I guess from the strict definition, no, we would never do that. But just in our loose interpretation that we have a bunch of zeros at s equals infinity, we do have two roots over here that you can see approach as s approaches infinity. But one is way up above and one is way down below. You should never have two over here. Okay? Should only have one that goes there. So it should only ever have one on the real axis. Does that answer your question? Okay. All right. So let's take a look at our plot now. So we have this closed loop transfer function, and we're going to use MATLAB to go ahead and plot it. So you can see what we just did in whiteboard is shown here. We have the 3 first poles, then we have a 0, and then we have another pole. Let's walk its way through. There's our asymptotes. Start increasing. You can see that the two closest to the j omega axis are approaching each other. The other ones are starting at poles and walking away and trying to end at zeros. And as k continues to increase, bigger, 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 we start to approach closer to our asymptotes. All right. Let's go back and see that again. Because take a look at the first thing I draw. I draw the asymptotes. You see they're at -4/3. You see the dashed blue lines? Those are both plotted originating at -4/3, and then they go up at whatever angle you have, plus or minus 60 and plus or minus 180 degrees, but we only have one at the plus or minus 180 degrees. And then my root loci start approaching those asymptotes at s equals infinity. Notice right here, see if I can do this fast enough. There's no asymptote that really exists over there, is there? Because it doesn't approach a 0 at s equals infinity. So even though I show one running through there, the root locus doesn't approach that. It ends at the 0. See if it'll keep going. Let's do that one more time so that we completely sick and tired of seeing it, because it's really helpful to understand when you draw these things, you know, what you're trying to accomplish. And this is just brute force. This is MATLAB plotting point after point after point after point to do that. That's what those red crosses are, is they're just showing you what the actual point is for k equal 1, 2, what on and on and on. And it's based on doing our closed loop transfer function and solving for the roots that way. Just about done. So essentially what I'm doing is I'm plugging in k in all these spots here, and I'm looking for the roots. So I start out with k equals 0, then k equals 1, k equals 2, k equals 3, 4, 5, all the way up until I don't care about the numerator because I'm not looking for anything in the numerator. I'm just looking for the terms in the denominator. Right? Does that help at all? Make sense a little bit of how we're trying to draw it? Okay. So to the right, that image is brute force, plug point after point after point after point after point. The left-hand figure is what MATLAB actually will draw for you. You can have MATLAB draw root locus plots for you. There is a root locus function. And this one's color coordinated. You can see the dark blue is going this way. The dark green is going over here. The red is the easiest one because it starts at a pole, ends at a 0. And then the last one going over to infinity is the light blue. So you can get color coding for the different root locus plots that you're looking for. All right, so I've been kind of sneaky, right? How have I been sneaky? Because if you remember when I started drawing this one, how did I know that the root locus started over here and started over here and went that way? Why didn't I put a root locus between those 2 points? I could have said, oh, well, let's redraw that. I certainly could have said, oh, well, Paul, let's just do this, right? Can't the root locus live there? And can it live over here like that? Well, first off, I know that can't be the case because this over here, right? That pole has to end at a 0. And why can't I have a root locus for this? Why can't this exist? Is there a rule, perhaps, that you all recounted maybe 10 minutes ago that helped me? Yeah, very good, Avery. It's not symmetrical because I know that I have to end at a 0, right? So if I'm going over here, oh, that's not a 0. So what do I need to do? I need to go away from the real axis. Can I do that? Avery just told me I can't, because if I'm going this way, I had better go that way too. And I only have one root locus plot between that point and the other point. I don't have 2. I only have 1. So I can't go like that, right? Doesn't exist. That's why I started drawing over here. So that's part of it, just understanding what you're looking at. The other thing is, where does the root locus live on the real axis? So let's take a look. So we know that for it to be valid, we have to have the equation 1 plus kg8 has to equal 0. And then my angle has to be either plus or minus 180. 3 times plus or minus 180, on and on and on and on and on. So the open loop phase has to be odd multiples of 180 degrees. So now I can go ahead and do the phase of my zeros minus the phase of my poles. By the way, why did I do that? Why did I say the phase of the zeros minus the phase of the poles has to be equal to that? We know why. This, when we solve this, right, we have KGH has to equal -1, which implies the angle of KGH has to equal that plus or minus 180, right, for the base one. Why did I say this right here? Why did I say it's the phase of the zero minus the phase of the poles? Any guesses? Let me add this to you. Remember, this becomes 1 plus K. You have a numerator over here, right? That's our generic one. That has to equal 0. So when we do common denominator, but really all we care about is the numerator, right? We're looking for the roots. So why is that? Why does that have to equal 0? Or why does it equal the phase of the zeros minus the phase of the poles? Let me give myself some room. Let me go back over here. So K, G, H has to equal plus or minus 180, or plus or minus, what's the angle? 3 times 180. On and on and on. I said that is the phase of the zeros minus the phase of the poles has to equal this, right? Oh, let's do dot, dot, dot. Why is that? Does that help at all? What's the angle of K going to be equal to? It's 0, right? Because K is a real number, isn't it? So it has to be 0. What is the phase of G and H? It has to eventually equal 180, yes. But how do I find them? Just by looking at angle GH. Would you agree with that as a numerator and a denominator? How do we divide complex numbers again? You remember that? Divide the magnitudes, subtract the angles. How do we multiply? Multiply the magnitudes, add the angles. So isn't this going to be the angle associated with the first one plus the angle associated with the second one plus however many you have minus the angle of the first pole minus the angle of the second pole minus however many you have. The reason why it's the phase of the zero minus the phase of the poles is because that's just complex math, right? we're subtracting or adding the angles based on the poles, because if I have S plus Z1 times S plus Z2 all over S plus P1 times S plus P2, and I asked you to give me the angle of this, what you would say is you would say the magnitude associated with Z1 plus the magnitude associated with Z2 minus, oops, the magnitude, not Z, the magnitude of whatever that pole one is, plus P2, isn't it? It's just complex math. We're just dividing complex numbers, which means or multiplying them, which means we need to add or subtract. And when we plugged in, remember before we did S plus 3 times 4J, that had a magnitude and an angle. That's all we're doing. We're just adding and subtracting. So that's what we have here. That's why it's broken out of the phase of the zeros minus the phase of the poles. So let's take a look at an actual transfer function with two finite poles and one finite zero. And we're going to stick a test point out someplace out, on the real axis and then see what we have. We want to see if that test point is going to actually exist on the root locus. So what angle do I need to get to that test point? 0, right? How about over here? Still 0. What about this one? Still 0. So the angle associated with the 0 over here to get to that test point is 0. The angle over this pole, not 0, is 0. The angle of this one is 0. So I've got my zeros, the angles of the zeros minus the angles of the poles. 0 minus the quantity 0 plus 0. Does that equal plus or minus 180 degrees? Doesn't look like it to me. So this is not a valid point on the root locus. This doesn't exist. Let's move my test point over here now. Let's clean up my mess here. All right. So what is the angle here? Or plus 180, right? So the angle over here is either plus or minus 180. What about over here? That one's 0. How about over here? 0. So when I calculate the phase here, 0, which is the angle associated with going from the 0 to that test point, minus 0 plus 180. Does that equal plus or minus 180? Sure does. So that is a valid test point. So anywhere to the right over here is no good. Anywhere to the left over here is a check mark. Okay. So on the real axis, so far what we've seen, anything to the right of that first pole is not going to work. So far, we've done 1 point to the left, and it looks like it's good to go. So my root locus, the rule is start at a pole and end at a 0. So we know once we're over here, we know that that's a valid point. We have to stay all the way over there. We can't leave because we don't have the complex conjugates, right? We're not symmetric about the real axis. So everywhere between this point here And this point here has to be valid root locus. Now let's do another test point. You do this one for me. Oop. Is this going to be valid? I'll give you 2 minutes. Is the test point now, is that valid? What was the approach that we did to see if it was valid or not? We checked angles, right? So what is the angle over here? 180? How about over here? So the angle of our 0 is 180. How about over here? Zero, right? All right, so now we're going to check to see if it's a valid point. So the zeros minus the angle of the zeros minus the angle of the poles. 180 minus 180 plus 0. Does that equal plus or minus 180? Does not. So over here is not a valid test point, is it? So it does live between this point 1 and this point 2. It does not live to the left of the 0. How about this last test point? 1 minute, do the calculation. Does it exist? We got one yes. He did the calculation in his head. Got a couple nods. Show me your work, or tell me your work. So you're saying P1 has an angle of 180. P2 has an angle of 180. Okay. Now let's check. The angles of the zeros minus the angles of the poles. Does that equal plus or minus 180? Yes, it does. So that means, clearing this up a little bit. It does exist over here. And Avery, why does it exist all the way over there? Because it's symmetrical, right? If I have one root locus, I can't just leave and go someplace else because the other end has to be there. So I have here and here, but not here and not here. Can you generalize anything about that? Look at the count on the real axis. 1, 2, and 3. Can you generalize a statement about when a root locus exists? Take a look at where the root locus exists on the real axis. What do you notice about the starting point? You see one starts here and one here, right? What do you notice about those?
Or sorry, if they're facing the 0.
Maybe, but that's more complicated.
Yeah.
I'm simple. Can I restate it the simple way? How about it exists to the left of an odd number? Isn't 1 an odd number? Doesn't it exist to the left of that? Isn't 3 an odd number? Doesn't it exist to the left of that? Always true. So on the real axis, oop, where does it live? To the left of an odd number only. Okay? How come it doesn't live right here? Because 2 is not an odd number, is it? 2 is an even number. So it doesn't live between 2 and 3 because to the left of 2, it's not an odd number. So this is a goofy one, but the only way that I know how to do it is to show you with these test points. So this is an important one, and why I was able to go over here and say, I know it lives between these two. Why? Because that's 0.1 on the real axis. This is 0.2. So I originally showing it lived over there. But between 2 and 3, we showed it as a blank, right? Between 3 and 4, hey, what do you know? We showed it living over there, but not between 4 and 5. Now, over here, you can say this is 6, right? But that's way out in infinity. So essentially, we just don't really count that because you don't go beyond infinity. But it lives to the left. This is only on the real axis. It lives to the left of an odd number. Odd number only. I got to pause here for a minute because it's simple, but it's like, what? How is that the case? You just saw it, right? We did all those test points and we did it just very rudimentary. And you can do any point you want. We already did this point. We did 1 point here. We did a point here, a point here, and a point here. And we just proved that that was the case. And it doesn't matter. We didn't pick the actual point. We didn't say it was 5.6 or something like that. We just said it was either to the right or to the left of an odd pole, or an odd polar 0 on the j omega axis. And we just saw for any point value it have, it would either be 180 degrees or 0 degrees. And so that's just the test that you do. That'd be a good test problem, wouldn't it? Have you do that, prove it? Or would that be too much? Have you do that during a test? What's that? But we just did this, right? And it was just 180 degrees. I mean, it actually isn't complicated math. It's, I mean, I know the concept might be a little weird, but when we just did it, it's like, wow, well, just 180 degrees or 0 degrees. I was like, yep, it just kind of falls out. That's why I like doing it this way, because you're like, oh, I see. Maybe you don't see, but you know, it doesn't, you don't have to be a rocket scientist to figure this out. You're just like, yeah, it's just plus or minus 180 degrees. All right. So can you help me out? Where is it going to live? Well, I label 1, 2, 3, 4, 5, and I always go from right to left, right? I'm always going in that direction. So even if you have some in the right-hand half plane, those count as your poles or zeros on the j omega axis. So we know it lives here, but not here. And we know it lives here, but not for the next one. And we know it lives here. And our rules are being met, right? Which is start at a pole, end at a 0. I'm starting at poles. I don't have any zeros on the real axis, but I get 2 root loci, which means I can have complex conjugates. So this one I can build a root loci or 2 root loci. Over here, I'm starting at a pole and ending at a 0. I'm good to go, right? I can build this one. And over here, I'm starting at a pole and I can't leave the real axis because I won't have complex conjugates, but I will end at a 0 way, 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 way out here at s equals infinity. Okay, so let me clean that up. And again, you can see that, just by doing the root locus. Okay. So if you want to say segments to the left of an odd number, however you want to say it, I just count them up and I just say 1, 2, 3, 4, 5, whatever it is. And I always go from left to right. odd to even, it exists, but not even to odd. So to the left of an odd number is where my pole zero map exists. How am I doing for time? I got a couple minutes. Let's do this. All right. So the last thing, I know I'm leaving the real axis here. I want to figure out, or I want to show how that one leaves the real axis. This is not one that I'd ask you to do for a proof, because this one takes a little bit of work. So in this system, we know that we have to leave the real axis, right? Because if we did our plots, we have something like this. So we don't have any finite or infinite zeros, right? So we have to jump off at some point and jump back on. And again, there's no root locus that lives there because it's not to the left of an, and actually let's check it. Well, let's do it over here on a bigger screen, if you will. So X, 0, and 0. 1, 2, 3, 4. First step I do, it lives to the left of an odd polar 0. So I know that whole way has to be root locus. Nothing between 2 and 3 because that's to the left of an even. Has to live to the left of an odd polar 0, but not to the right. So we know it lives there. And it doesn't live beyond 4, which is okay because for root locus, we have to start at a pole end at a 0. So we know it has to do something like this. It has to jump away from the real axis and then eventually jump back in. These points are break in or break away points, just depending on your perspective, right? If you're jumping off, you're breaking away. If you're jumping on, you're breaking in. All right, so we already did this. We just did that here, right? So we know that that's what our base is, and so we use our root locus. We also want to use the rules that it starts at a pole, ends at a 0, which means we can add on our zeros to start, and then we end over here, right? So that tells us we have to jump away. What about this root locus? Do we apply rule number 3 here? Would rule number 3 be applicable here? Avery says no. Anybody agree with her? I agree with her. Because what is an asymptote? An asymptote is when you approach a 0 at infinity as k approaches infinity. I don't have any zeros at s approaches infinity, or s equals infinity, do I? Because n equals m. So n minus m is going to equal 0. So I don't have any asymptotes. So you don't even have to use that one. Okay? So one of the things you're doing when you're building your root locus is try to figure out, what are my basics? I always should have some poles or zeros on the real axis. And then, so I can start to draw that out. And then you have to start to see, will I move away from the real axis or do I just stay on it? Because if I stay on it, I don't have to do anything, right? I don't have to calculate asymptotes. I don't have to, calculate breakaway points. I don't have to do the centroid of those asymptotes. I don't have to worry about it. So in this one, you can certainly do the root locus, but what you would do is you would divide by 0 over here, right? N minus m would be 0, so you're dividing a number by 0, so you wouldn't even be able to do it. So don't do root locus 3 if you have root locus rule 3 if you have no infinite zeros. All right, so this is going to be an image to show you as k approaches what's going to happen. So take a look at these plots because you're going to see what ends up happening. Here's k equals 0. K equals 0.7 when they break away, or 0.07, and we'll see why. We're going to continue to increase k until it becomes real again. That's k equal 14, and I'll show you where we get the 0.07 and the 14 in a second. We're going to increase k, and then eventually we're going to go over here. So what do you know? You allow k to start at 0. and then you approach k equals infinity, and then you see what the points are. So let's take a look. Here's a plot of k, actually what's happening. Go back up. Do that again, because it's very important. Look at what k is doing. So the first plot is what happens between the two poles. Look what happens at k when they leave. Now do the same thing for the other two. Look what happens. The second one was more subtle. Try it again. Don't worry too much about the first one. You saw how as it approaches, look at what happens with k, but then the second one happens very quickly. So you might want to focus on the second plot. What do you notice? What do you see? What I see is when that plot of my gain reaches a peak point. In either case, right, it's either a positive peak or a negative peak. It's when I'm either leaving the real axis or I'm entering the real axis. Isn't this, see if I can get this quickly. Where is it? Why does it want to annotate? Damn it. It didn't want to annotate. It won't annotate. Sorry about that, folks. Okay, I think I paused it. That point over here corresponds to when it was leaving the real axis. That point here corresponds to when it enters the real axis. Okay? For our math whizzes, when you are at those 2 points, when you're entering or exiting, what's a way to solve for those points? It's calculus 126. Pardon? Taking the limit close. How do you know you've reached a maximum or a minimum point in calculus? Say it again. Possibly. What's another way to say that that's even easier? What is the slope of this line right here? So when the derivative equals 0.
Yeah.
So I wasn't picking on you. I'm literally, it's like you said, when the slope, the sign changes. I'm like, how about even easier? Just say when it equals 0, you know it's going plus, then it goes to 0, then it goes to minus. So the easiest way is to take the derivative of a function, set it equal to 0, and you have a max or a minimum point. That's what we're doing over here. Let me see if I can skip through here. All right, so when I take the derivative, I'm going to get a k max of 0.07. And that's when I just leave the real axis. When I do another derivative, get the 0, I'm going to get the minimum. Here's my characteristic equation. So I'm going to solve for k equals -1 g times h, and I'm just going to take the derivative of that. So that here, and don't get nervous. Everybody know what this symbol is? I'd pick on my 420. The students have taken 422 with me because we did it a bunch. It's a derivative symbol, but it's a partial derivative symbol. Everybody know about partial derivatives? So if I have an equation, and unfortunately, you only get this in vector calculus. They don't do it in Calc 1 and Calc 2. It'd be great if they would do it because there's a lot of engineering that you do partial derivatives. So if I have 3xy plus 2x squared plus 4y if I want to determine the sensitivity of that equation to changes in X, I'm going to take the partial of that with respect to X. What does that mean? Sensitivity is saying as X is changing, how much does that equation change? It's of X changing, not Y. So X is moving, but Y is a constant. So this just becomes 3Y plus 4X plus 0, right? Because 4 times Y, if I'm allowing X to change but not Y, then 4 times Y is a constant, right? So the rate of change of a constant is 0. Then if I do the same thing again, so when you do partial derivatives, you can do them to every variable. I get 3X plus 0 plus 4. Okay? So you have to go back to what a derivative is. A derivative is just a sensitivity to how something's changing, see what happens. Pausing here because I recognize that probably most of you in this class have never seen partial derivatives. Good question. So for those of you in TV land that didn't hear, why does the Y in the first partial derivative look differently than in the second? Because, and this is going to be hard to show, right? 3x times y, if I had to look at it in just 2 dimensions, has a slope of that, right? It's 3 times y. So this slope, and again, I'm drawing it 2-dimensionally, I'd have to draw it 3-dimensionally. So what is the derivative of that? It's this, isn't it? It's a constant 3 times y. Over here, 2x squared, what is the slope of that? It doesn't have any slope with regard to y. It's not multiplying y. So it doesn't have any impact. It's not affecting it. So it's not that it's changing anything. It's just the fact that it doesn't multiply x. And so as I vary x in that first case, it doesn't change anything. So over here, it's 3y. In the bottom one, when I take the partial of 2x squared with respect to y can change all day. And this thing is not going to change in any way, shape, or form. So no matter what I do to change y, it doesn't care. That's why that goes away. It's not, it's a fixed value, it's constant. So there is no rate of change. It's 0. Up here? Okay, so if I was to plot this x, the slope, right? Or actually I'll put x over here. And time, if I wanted to get dx dt, then that's changing 3 times y. Over here, if I have 4y, that's a constant, right? Oops. Y isn't changing when I'm taking the partial with respect to x. So this is 4y, this is t. How much does dx dt change? It doesn't change at all. There's no change. Yep. So partial derivatives, again, I wish we would cover it, but we don't. So this is where the math can get a little ornery. So all we have to do is take the partial of -1 over g times h and evaluate, or we're actually going to solve for it here, the sigma term, because that's where we're trying to figure out where we're due. So we're going to take the partial, once we substitute in our s term of this you have to do the chain rule, right? Or is it quotient rule? I think it's actually just the quotient rule to go ahead and do it. So that's when you take the partial of n times the denominator minus the partial of the numerator, and what you end up with is a pretty ornery equation here. Then you're going to combine that over here. You set that equal to 0. And I've got 2 points. -3.366 and -1.634, right? Those are the two. I don't care about this denominator term because when I multiply both sides, it goes away. And when I divide, so I only look at the roots of that equation there. So I have 2 points, a breakaway point and a break-in point. So minus 1.634. Let's go back up. So minus 1.634 is that point right there. That's minus 1.634. The next point is minus 3.36. Minus 3.36. Those are those 2 points where you break in and break away. Now, sometimes this equation can get pretty crazy, and you might have, a bunch of more points over here, okay? Some of those points are going to be invalid. How can you tell if they're invalid? Well, if I have a point that ends up over here, do I break in or break away at that location? No, there's no root locus there. So this point over here would not be valid. So one of the things you have to do when you're trying to solve for the break-in, breakaway points is you do have to sometimes figure out, are those points actually valid or not? These two were pretty easy. You only had 2, so they both had to be valid. This probably is the hardest thing about doing this work, is calculating these, because you got to do the derivative, okay? And unfortunately, you always have to use the quotient rule, because you almost always have a numerator and a denominator that are different. So you will have to do it. I will suggest that you FOIL everything and expand everything out as much as you can, because taking the partial derivative of this or the derivative of that is not too bad. But if you had to do this and take the derivative of this, that's a little more difficult, right? Because then you have to use the chain rule. You have to take them and do it that way. It's just easier to just go ahead and s squared plus 7s plus 12 and find the derivative of that. That's usually much, much easier to do it that way. You can, if you want to. You think you have to do it symbolically, right, to be able to set it up on your calculator? I don't know. So if you want to, that's fine. It's not a difficult derivative, but you want to check your work, yeah, that would be fine. Okay. And if you want to solve for the values of K, you just plug in your sigmas, and then you see what those values of K equal, and you get negative, or you get positive 13.9 or 14 or 0.077. Remember how we said over here, how did we get this number and that number? You get it from finding those values that result in a derivative of that term going to 0. Okay. So those are our points. We've got this value here, 0.072, 13.9, written a little more accurately. And then we have these values of where they actually leave. So at S equals negative 1.63 and negative 3.4, that's where we break away or break into the j omega axis. But it's super, super important to be able to draw this and go through our first few steps to know that our root locus lives here and lives here, because you have to have intelligence to say where my breakaway points are and are they real. So this is really, really helpful, I think, for some people to be able to determine, all right, here's where I break in, here's where I break away. So that's rule number 5. Okay. Now, do you always have to employ rule number 5? No. If you never leave the real axis, why would you calculate break-in or breakaway points if you never leave the real axis? So what we're trying to do is we're trying to do this step by step, because this is our 5th rule. There's a lot of rules that if you can go through them and hopefully in order, you might be able to simplify your work. Do I need to calculate angles of asymptotes? Not if I never leave the j omega axis, the real axis. Do I need to calculate the break-in or breakaway points? Not if I ever leave the j omega, the real axis. I don't need to employ those rules if I can look at my base figure and make a determination about, yep, I'm leaving or no, I'm not. Okay? So that's why when you're building these root locusts, it's really important to start to build them slowly and then see how you end up. How's my time? Out of time? I'm out of time. Look at that. Make sense? Doesn't make sense? Because we're getting to the point, right? We won't have a test next week. We'll have a test the week after, right? Because we can't have a test the last week of classes. So we've got 3 more weeks of classes, which means not next week, but the week after we have a test. And we'll be focusing on root locus. And so we're almost done. We're got 10 or so more slides to go. We'll do an example and we'll start prepping for the 3rd exam. Go from there. Any questions in TV land? Nothing? All right. Have a great day, all, and I'll see you around. Take care, everyone.